Hi, everybody. Last week we talked about how to calculate observable quantity in terms of the amplitude, as I listed here. Okay, and the main technical thing is that in the amplitude we have a delta function, and when you square it to obtain observables like cross-section, decay rates, which are probabilities, then you have a delta function square. So in principle, they will lead to infinity. However, as Tom has said in his notes, this is actually a manifestation of the fact that we calculate in an infinite volume and in infinite time. However, this is not what really happened in our experiment. We couldn't observe the experiment for infinite long, and as you all know, that the collision only happened inside the collision point of accelerator. And therefore, actually, what we are observing is not the probability for infinite long for the whole universe. What we are calculating is the probability per unit time and per unit volume. So after you carefully put in all these practical consideration, actually that the infinity will disappear from your expression. So very nice. And so therefore, in the final expressions I gave you last time, we arrive at a very clean expression for the decay rate and the cross-section. And you here got only one delta function left in your expression. And here the amplitude is the amplitude with the delta function taken out. Sometimes we call it the invariant amplitude or Feynman amplitude. This is the transition amplitude when the delta function is taken away. Therefore, we arrive at a meaningful expression to do practical calculation. Very nice. However, as I told you last time, we still have some problem with the amplitude itself. So let's return to the amplitude for a while. That's what we are going to take care this week for about 30 minutes. I'll try to make my presentation a little bit brief. However, I put all the detailed explanation in the PowerPoint. So I will encourage you to read after you listen to this lecture, and I think it will benefit you a lot. Because I will try not to waste your time by talking too long. Okay, and some of the proof or presentation will be very awkward if you done online, even in class. Therefore, reading the PowerPoint probably will be much more useful for you to comprehend what's the subtlety in this very exciting topic. Okay, so amplitude. Remember here the amplitude here is the S matrix or the transition amplitude from a certain state in the far past to the long future. However, these states, as you may remember, we create and annihilate with an operator, the creation operator or annihilation operator, which belongs to the field operator in interaction pictures. Therefore, these states in the far past and the long future are eigenstates of H0. That's the free Hamiltonian, because the field actually evolved in this interaction picture in terms of the free Hamiltonian H0. However, this free Hamiltonian H0 is not the whole Hamiltonian. Okay, but in the initial states and the final state are supposed to be the eigenstates of the whole Hamiltonian because, well, I mean, that's what you want to ask. The particle are the particle states that participate in the collision should have been the eigenstates of the whole Hamiltonian. But however, you can sense that why we do it does not raise your doubt earlier, because in your imagination, in the far past, as this cartoon showed you, in the far past, actually the eigenstates of H0 are the same as the eigenstates of Hamiltonian, because in the far past, all these colliding particles are not interacting with each other yet, because they are still traveling in the accelerator, right? So they are not interacting at all. So it's almost safe. It's intuitive that we can suppress or ignore the interaction in the far past when these colliding particles are not interacting yet. And in the far future, after the collision, I mean, they don't interact at all, because we are detected that they are separated with each other, no interaction at all. So that's why it does not raise any doubt to you that that we choose the eigenstates of the free Hamiltonian in our calculation of scattering. They should have been the eigenstates of H, but we choose the eigenstate of H0 to do calculation. So therefore, Tong in his lecture notes make a very important assumption in his passage. He said that the initial and final states are eigenstates of the free theory. That is, as I say, the eigenstate of H will be identical with the eigenstate of H0. And to make this assumption more concrete, it is technically in literature, it is always called or usually called a diabatic condition. Let me stop here a little bit to tell you that in this presentation, I will follow very closely lecture notes by Sidney Coleman. In addition to Tong, we have been using it for quite a long time. Sidney Coleman is one of the greatest particle physicists in the late 20th century. And he taught, in addition to his other contribution, I will not go into detail, he taught a very famous quantum field theory in Harvard physics department of Harvard University. I'm lucky enough to serve as one of his teaching assistant for about 2 years. Very nice lectures, and it is rumored that almost all the graduate students in the Boston area, including Harvard and MIT, attended his quantum field theory course. So he used his own lecture notes, and they are usually photocopied and distributed for a fee at the beginning of the semester. But later, in the 2013 or sometime around that, a student finally tried to type up all the lecture notes into a comprehensible notes. Here you can see the archive number, and you can download it yourself, and I will try to give you the page number when I proceed. Okay, and in this part I will follow very closely his lecture notes. Okay, so this is, and Sidney, Professor Coleman invented a very, I think, very good terminology. He called it the low energy scattering theory. Low energy means it's low budget. Sorry, it's a low budget scattering theory. Low budget means it's not good enough. Okay, but wow, I mean, if you haven't had any money for a Porsche, then you probably will try a Camry or whatever. So it's called low budget, but it works. That's the point. And so today I will present the low budget scattering theory and present the high, did he call it? High energy, high budget? Yeah, maybe. Oh, we'll see very soon. The high budget scattering theory together, so that you can see what's the point here. And before we proceed, the bottom line is these two theories actually give the same answer. That's why if you don't want to go into that much theoretical detail, or you just forgot all the theoretical subtlety, you can just go with the low budget scattering theory. A lot of authors did this, okay, in their lecture. Okay, so the low budget scattering theory is essentially the so-called adiabatic condition. Again, let me remind you, during the scattering in the far past, there's no interaction at all. In the far future, no interaction at all. Why don't we just make approximation that we turn it off? Exactly, that's the adiabatic condition. So as I listed here, as Professor Coleman presented here, he defined the H to be the free Hamiltonian plus the interaction Hamiltonian, however, multiplied by a function of time. And this function of time is equal to 1 during most of the time, however, falls to 0 in the far future and falls back to 0 in the far past. So it actually just make explicit the assumption I told you earlier. Before the scattering, after the scattering, there are no interaction at all. Okay, so sounds reasonable. So that's why this adiabatic condition or adiabatic assumption actually feature in a lot of quantum field theory textbook. Okay, so if this is, and you can follow the Professor Coleman's very detailed discussion in the lecture notes I listed here. Okay, but I will not go into detail. Anyway, but the point is, if you assume this adiabatic condition, then now in the far future and the far past, H is equal to H0. And what we did during the earlier calculation is justified. That is, the initial and final state are eigenstates of H, supposedly, but they are also the eigenstate of H0 in the far past and future because H is equal to H0. So what we did is justified. Okay, so then we can now finally list our final expression, and no problem at all with the amplitude. The amplitude, scattering amplitude from state I to F will be da 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 da. I hope you are familiar with this expression already, and it will be equal to roughly the sum of all Feynman diagrams with on-shell external momentum. Okay, so I don't, in this course, I didn't go into detail about the Feynman rule, but I suppose you have already learned that in Professor Chen's lectures. And so what I said here is, so I assume that you are familiar with the rule of how to write down the Feynman diagram and write down the Feynman rules for every the Feynman amplitude for every diagrams. So what I do here and define here is that this scattering amplitude is equal to the sum of all the Feynman diagrams with on-shell external momentum. And then you can plug in this expression into what I have in the detail, in the decay rate and cross-section, all these observables, and you got the final answer. So that's essentially what I call the low-budget scattering theory, and it works. Okay, it is actually what the particle physicists do almost every day. Okay, write down the Feynman diagram and calculate, and boom, you got the observables. Okay, but it's a beautiful picture. However, even before we feel safe, there are two remarks I need to remind you. First, for this low-budget scattering theory to work, we still need to assume something. Because in the far future and in the far past, H is equal to H0. That means the spectrum of H0 must be the same as H. Remember, H does not change at all. Okay, so you have to adjust H0. You cannot choose any H0 in your calculation because H is a fixed thing. That's the whole Hamiltonian. And it had a spectrum. This spectrum corresponds to the particle you observe in nature. It's consists of the mass and and we know before we do any calculation that the eigenstate of H, the whole Hamiltonian, must satisfy energy is equal to P squared plus M squared with a certain physical mass. Therefore, the mass parameter, I call it mass parameter because in H0, it's not clear. The mass parameter is the same as this M. Actually, what we will do in the next couple of weeks is to do renormalization. And you will see that in renormalization, we actually separate the M or mass parameter into two parts. One of the parts will be infinity to cancel the infinity in the amplitude. But that's for the next couple of the weeks. But I could say that you have to remember the parameter, the mass parameter in H0. Of course, we also call it M. But remember that M does not need to be the same as the physical mass. That is, and therefore, this assumption for the low budget scattering theory to work, we need to make sure that mass parameter agree with the physical mass of M. Okay, this is very subtle difference. Okay, yeah, and it will have very, very important implication in renormalization in the next couple of weeks. I will show you when it comes. But remember first, you have to remember this in your mind that you cannot choose this H0 arbitrarily. Okay, its mass parameter must agree with the physical mass. Okay, so but it's not hard to do. I just follow the rule. Okay. However, there are even more problems in this low budget scattering theory, as Tom listed very clearly in his notes. I would probably just read the passing. Yeah. First of all, obviously we cannot cope with bound states. Obviously, okay. Yeah, because without interaction, there is no bound state. Therefore, for example, this formalism cannot describe the scattering of an electron and proton, which collide, bind, and leave as a hydrogen atom, because you assume that there's no interaction in the future. So there is no hydrogen atom, there's no bound state in the future. Okay, so that's why that's the first very serious drawback, shortcomings of this low budget scattering theory. And even more important, a single particle a long way from its neighbor, that means it's totally alone. Okay, and before the scattering or long after the scattering, is never alone in field theory. Remember, it is true even in classical electrodynamics, where the electron sources actually emit electromagnetic field from which it can never escape. Put in the simple words is that even though in the far future and in the far past, when an electron is alone, it is still clouded, or it is still clouded by photons, virtual photons. Okay, therefore you cannot really turn off the interaction. If you turn off the interaction, the electron is no longer itself. That's the key point. That's a very, very important key point. Okay, again, this key point will feature again in the renormalization program. Okay, so I will come back to this second later. Okay, but remember these two very serious drawback, especially the first one. And the first one is almost fatal. I could say that. So in quantum field theory, we usually could not deal with bound state, and of course, one of the problem is that it's most of the time perturbative. But it is also that intrinsically to the formalism, we kind of turn off the interaction. Okay, now then if you would turn off the interaction, there is no bound state at all. Okay, so that's why it's very, very hard to deal with bound states. You can remember that in quantum mechanics, bound state actually is the first physical system you calculate the hydrogen atom. However, in quantum field theory, well, forget it. We even don't know how to calculate hydrogen atom. Okay, so but that's fate. What could I say? Okay, now the end of the low budget scattering theory. Now the luxury. Oh, so yeah, that's the word I use. The luxury scattering theory. In Professor Coleman's language, is a reformulation of the scattering theory with no more turning on and off. Remember, the low budget, the basic feature is this turning on and off function of f to turn off the interaction. And here I say that you better not do the turning on and off because there are some drawbacks. So now we present a luxury scattering theory. But the luxury scattering theory needs some is a very subtle. So therefore, I need to leave the question here and go to discuss another thing first, and then come back to the conclusion in the end of the lecture. But when I go this detour, actually I introduce a very important thing. We call it Green function in quantum field theory. The bottom line is listed is outlined here by Tong. Most of the application of quantum field theory is related to the scattering experiment, but not all. A lot of the other application, in a lot of the other application, the physical observables are not scattering. Okay, we usually sometimes could we sometimes need to calculate something else. Okay, and these other physical quantity usually consists of the so-called correlation function or Green's function. In particle physics, we usually call it Green function, but in the condensed matter theory, as you know, that the quantum field theory is also essential for the many body physics, surface solid state physics. They are usually called the same kind of thing are usually called correlation function. Okay, therefore, when I talk about Green function, you probably need in your mind know that these functions are also useful in condensed matter theory. So that's why in a lot of textbooks, especially those textbooks who advocate that the quantum field theory is not only useful in particle physics, but also in condensed matter theory, they actually use this correlation function or Green function a lot from the beginning. So it becomes it becomes celebrities these days in quantum field theory textbook. Okay, so let me again present this Green function using Sidney Coleman, Professor Coleman's lecture notes. So again, as I have said earlier, the S matrix is equal to the sum of all Feynman diagrams with on-shell external momentum. And to set the terminology, we define this thing roughly. There are some subtlety, but let's forget about the subtlety here. We define the sum of all Feynman diagrams as Green function. And here, this Green function, this Feynman diagram has external lines whose momenta are on-shell. Therefore, we call it on-shell Green functions. So the point is, Green function, the concept of Green function can be extended to off-shell Green functions. In Sidney Coleman's words, he wants to consider Feynman diagrams with external lines off the mesh shell. Well, so here I probably just read his explanation. He is so good at explaining things. So Sidney assume this blob Feynman diagram. That means anything could happen. I'll give you some example later. So anything could happen in this black gray blob, and with, for example, 4 external line, so we call it G4 because there are 4 external line, and with momentum K1, K2 to K4. Represent the sum of all the Feynman diagrams to order. I mean, it could be all Feynman diagrams to some order in perturbation theory, or in our imagination, the sum of all diagrams to all orders in perturbation theory. So he posted a question: can we assign any meaning to this blob if the momenta on the external lines are unrestricted, off the mesh shell, maybe not even satisfy K1 plus K2 plus K3 plus K4 equal to 0, off shell? Okay, when I call on shell, that means K1 squared is equal to M1 squared, K2 squared equal to M2 squared. Okay, that's what happened when this diagram is applied to the calculation of scattering theory. And if you may remember, that's because in calculating this transition amplitude, we use the annihilation operator to annihilate this I. And this annihilation operator has consists of momenta which satisfy on-shell condition, first of all. Secondly, this I, the external particle corresponds to initial states or final states. And initial state and final states are observable, so they are particles, so they must be on shell. So at first you will say, wow, how could you consider something that does not exist? But first of all, you have to remember first, well, could I do this? Even though it does not apply to nature, but could I do this mathematically? The answer probably is yes, because we have rule. We have Feynman rule. So how about we forget all the origins of this rule and simply take these rules as given and then apply to something like this blob and calculate without knowing, without considering what's the significance or what physical meaning of these things. Possible, right? Yeah, so it's just mathematical. Well, that's the beauty of doing the physics. Well, you can consider something that's not physical mathematically. Yeah, so again, first you have to remember, you have to adjust your mindset that when doing this, we are calculating something mathematically without considering whether it is physical or not. That's the first point. However, Sydney is going to come up with 3 answers, affirmative answers to this question. That means, well, even though I say it's only mathematical, but it has some physical meaning. Got it? Okay, so mathematical, could I do this? Of course, yes. But physically, it is also useful. Okay, and Sydney continue to give you 3 answers. So we'll follow him and give you answer 1, answer 2, and answer 3. And because Sydney did a much better job than I do in presentation, so I will just I almost follow his presentation and only briefly commented on the important points. And I will encourage you to at least glance over his lecture notes and jump on some of the beautiful part of the beautiful presentation, and I think you can learn a lot from that. Okay, so answer 1. Wow, it's so obvious. Answer 1, again, what's the question? Could this blob make physical sense if the external momenta are off shell? Well, it could be internal part of a more complicated graph, right? Of course. For example, here in this diagram, here you don't need to. Well, it's you don't need to know exactly what kind of a model it is. However, these are the rule. We have a 3-point vertex serving as interaction, and here we are talking about a 4-point. Of that Feynman diagram, usually we call it four-point function because they have 4 legs. So 4-point function is here. 4-point function. And if I calculated using Feynman diagram, this diagram has to be included, right? Yeah. So this, and this. Well, you don't need to go into detail. The only point you need to remember is that they could all be included in a blob. As I say, this blob could be anything. So dot 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 could be summarized into this. Of course, with this blob thing, we still don't know how to calculate, but at least we know how to collect them into something in the middle. Okay, so and this is, if you look at this middle, then it is the so-called Feynman diagrams with external lines, because as I said in our lecture last year, I suppose, if these lines are internal line, they don't need to be on shell because they are in the propagator. In the propagator, it does not need to be on shell. Okay, so again, the blob could be an internal part of a more complicated graph. Okay, this is a very obvious answer, but it doesn't give you too much. But before we go on to the answer 2, we're using answer 1. Let me define another useful form of these function as the Fourier transform. So Cindy say we can use it to obtain another function. It's Fourier transformation. Fourier transformation is the momentum space function times exponential ikx and sum over all the momentum possible. And it gives you a function of the space-time. So it's from your second year mechanics, the Fourier transform. And then you can inverse Fourier transform back into fk by multiplying the space-time function with exponential minus ikx, again, the plane wave function, and do the integration over space-time, and you come back with the momentum. So I can do the same thing. Here, I can we can Fourier transform the green function we discussed. So with the green function, with the did I call it the green function yet? Anyway, it's it's green function. Okay, but so far it's only the summation of all the Feynman diagrams But let me just call it green function. So the green function in momentum space k1, k2, kn, you can multiply by this collection of plane wave and integrate it over all the momentum and get a function of the space-time. Okay, so I think it's very clear. Okay, and you can see all the detail. And here I also list the page number in Sidney Coleman's lecture notes so that you can follow on your own. Okay, so this green function. This is the green function. And now this green function is in the space, in the arguments of this green function are in space-time. So if you have already taken some course in condensed matter theory or solid-state physics, or statistical physics, this kind of thing is actually very similar to at least the mathematical form becomes very, very similar to the correlation function you have learned a lot from these courses. Okay, so in the end, they are indeed identical. Okay, so this I will sometimes just call this space-time green function, and this the momentum space green function, but they are just the Fourier transform of each other. And now answer 2. In light of answer 1, we can have answer 2. What we did, and actually it's very, very useful. I probably, if Professor Chen has already covered this part, the so-called generating function now, you are familiar with this row already. Okay, so it's the same thing. It's just what you learn in the quantum field theory about the generating function now, and I will come to the generating function now very soon. So we get an answer 2. In answer 2, what I did is to add a source to this quantum field theory, rho. So rho is a C-number source, not an operator. And we usually like to call this rho a probe, like I stimulate the system a little bit and see what the response is. And during this stimulate response, I can learn the physics of the whole system. Okay, that's the physical image of the whole thing. So I add a rho times phi. So this rho, the source, will be connected to a field. Okay, and let me put it more clearly. This rho is a function of x, so that this rho could carry some momentum, full momentum. Okay. Now, with the introduction of this interaction rho phi, that means you get one more vertex. This vertex is dot connected to phi. So I think if you are familiar with how the Feynman rule and Feynman diagram are derived, this does not surprise you, okay? And so you can convince yourself, and if not, then Feynman, Coleman's lecture notes has a very detailed, he called Model 1. You can go back to the earlier parts of the lecture note. He has a more detailed discussion of how to add this kind of source. Okay, but I assume that you are familiar with Feynman rule and Feynman diagram. So this interaction corresponds to a point. This point is the external source generating, annihilating a phi particle. And after and the Feynman diagram, the Fourier transform of the multiplication of two functions is equal to the multiplication of two of their corresponding Fourier transforms. Therefore, rho phi will be equal to the Fourier transform of rho times the Fourier transform of phi. And the Fourier transform of phi are essentially the creation and annihilation operator. So they are used to create or annihilate this line. Therefore, the Feynman rule corresponding to this point is rho tilde, is the Fourier transform of rho. Okay, so this interaction generate or give rise to this vertex. So now we use this theory to calculate the amplitude of vacuum evolving into vacuum. I mean, evolving into vacuum should better be described as staying at vacuum. Of course, if it is vacuum, then it stays in vacuum. However, with a source, it could evolve into something else. For example, it could excite one particle, excite two particles. That's what the rho could do. So here we are going to calculate the amplitude of vacuum staying at vacuum or evolving to vacuum. Okay, so this is this. In the far future is zero vacuum. In the far future, in the far past is vacuum. After the transition time evolution, it becomes stay at vacuum. And this kind of this amplitude equals diagrams with no external lines because there are no particle. The initial particle has no particle, initial state has no particle, the final state has no particle. So therefore, no external lines, only internal lines. However, we can have line ending in source. For example, to the leading order, we can have this diagram. Okay, so indeed, we have one diagram like this, dot, dot, dot. Okay, and here, we sometimes call it tadpole, tadpole. Diagram. Okay, look like a tadpole. Okay, and to the order of g cube, we will have this. That means somewhere in the middle, then this particle could split and becomes a something like this. But it is proportional to rho because there's only one dot in this diagram. One dot corresponding to one rho. But at rho square, we can have more diagram. For example, at rho square, we can have this rho. You can see the diagram here. Okay, as well as if you have two rho, you can have two tadpole and some other fluctuation in the vacuum. Okay, so or this one also, this two row, two dot connecting by one propagator. However, in vacuum there are some fluctuation. There's no external line, no internal line, only two source. Okay, how good. So these examples give you some sense about how we draw Feynman diagram in this. And the surprising thing is that then to the nth order of row, actually you have a diagram like this. Not one diagram, but you can collect all the diagram in terms of a blob we mentioned earlier, isn't it? That's the key observation. To the nth order of row, you can of course compare to what we have here. To the every order of row give you a dot, and every dot give you a incoming particle line. But this incoming particle line doesn't need to be on shell because it's actually internal. That's the point. Okay, so that's essentially answer one. I say that the the blob could be an internal part of a more complicated graph. Indeed, that's exactly what happened here. This blob is the internal diagram which involve more complicated external sources row. Okay, yeah, I hope you can see the connection. But the bottom line is to remember all diagrams, that means you use Sydney's words. This blob will denote the sum of all diagrams to order G, to all order, sum over all G. And the point is that that's at the nth power row. If it is at the nth power in row, that means you have n dot. Okay, and if it has n dot, you have n external line, but this external line is corresponding to a blob. In terms of whole diagrams, they are internal line. Therefore, the momenta could be offshore. Okay, so I hope you catch it. So with this, this is a contribution to the vacuum-to-vacuum transition amplitude. Therefore, if you sum up all the possible diagram or all the possible blobs like this, then you can arrive at finally the whole of this transition amplitude. Okay, so you can say that the whole transition amplitude will be the sum of various terms with row at various order times the corresponding blob. Okay, sorry, I jumped too early. So if this diagram is the blob, then if I call this blob the momentum space Green function, then every blob contributes to a row. So the Feynman rule for this diagram is G times row. I hope you see my point. But the K now is internal, right? Is internal. And you remember your Feynman rule. For internal line, you do the integration. So you got a K1 integration, K2, blah, 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 until Kn. And Sydney actually spent a lot of time to work out the combinatorics arguments. So I'll leave it to if you are interested. But the bottom line is they works. Okay, so the bottom line is these diagrams is equal to the blob, the Green function I mentioned, times the row to the nth power and taken with the integration. And therefore, sum up these diagrams to all order of row, you got this expression very beautifully. Still, of course, you will say, well, I still don't know how to calculate G, but at least we get a physical meaning, an answer 2 of this G. Even more important, remember the multiplication of function is equal to the multiplication of their corresponding Fourier transform. So this whole thing, I leave it to, if you want to prove it yourself, but it is part of this expression. Then we can Fourier transform the whole thing into rho x1, rho x2, rho to up to rho xn times the green function of space-time x1, x2 to the xn. So this is the key expression of this part of our presentation. Then we call it, let me remind you that this transition amplitude is vacuum to vacuum, however, under the influence of a source rho. So it's better to write S0 with a subscript rho, so that you know it's not a vacuum to vacuum transition, but a vacuum to vacuum transition under the influence of rho. It is useful to define this whole thing. Of course, this transition amplitude depends on the function rho. Okay, so it's called a function now, and this is called z. Okay, usually called z. So this is a z function now of rho, and this z function now could be expressed in terms of a expansion in rho to the nth power. Okay, so you just imagine it is the Taylor expansion with a x integration. I hope you can convince yourself when you differentiate z over rho x1, rho x2, then what you get is the green function x1, x2, and to xn. Remember, when you do this delta function, then this x1 must match the x in your expression, and therefore that's why the green function you get here, the space-time argument corresponds to x1. So it's usually better if I got a prime here, x1 prime, x2 prime, x1 prime to xn prime, x1 to prime, xn prime, to make this clear. But I think you could do it in your mind. Okay, so that means we arrive at a function now that keep track of all the green function. Remember, so Feynman here say all the physical information, including all green function and hence all the S matrix element about the system, is coded in this vacuum persistence amplitude. That's what I call vacuum to vacuum amplitude in the presence of an external source. That's beautiful. That's beautiful. Even though we haven't arrived at any new conclusion or any new thing, however, to summarize all the physics in terms of one functional is astonishing, surprising, and exciting. Okay, and it is also useful because from this z you can easily obtain the generating function for connected Feynman diagrams. Yeah, because I think Professor Chen has already covered this. The sum of all Wick diagram, that is all the Feynman diagram, is equal to the exponential of all the connected diagrams, but of course the normal ordered. Okay, therefore z rho, if you take log, then it corresponds to the connected diagram the connected diagram. Therefore, this G now is connected diagram. Okay, so with Z, you take a log, then it could generate all the green function with only the connected diagram. Yeah, I didn't do bad. I did much worse than Coleman, so let me probably just read his notes. The GC, this is true because the terms in the sum, in the exponential, are themselves normal ordered, and convince yourself, and taking the natural logarithm, And this GC is the sum of all connected Feynman diagram with K1, K2 to Km, possibly offshore. Okay, and yeah, so that means log z would be the generating function now of connected Feynman diagram. Okay, yeah, please follow a little bit what Coleman say. And actually, it is this kind of connection is also covered in almost every quantum field theory textbook, including Ryder. So you can also consult that book. Okay, so that's answer 2. Here, I introduce a source connecting to phi and calculate the vacuum-to-vacuum persistence amplitude. Let me remind you, in this calculation, I'm working in interaction picture. Interaction picture, I mean, you separate the H prime interaction. Here, this vertex. Interaction. And you treat this interaction and rho phi, the new source phi vertex, as the interaction. Okay, so I treat H prime and rho phi as the interaction Hamiltonian, and therefore we have two different kind of vertex, and H0 is the free Hamiltonian. So that's why I call it, we are working in the interaction picture. However, we can also work in the Heisenberg picture of the whole Hamiltonian. Okay, Hamiltonian H, not the whole, but the part of the Hamiltonian in additional to the rho phi. That is, we treat the rho phi as the interaction, but include the original interaction in H. Here, say it much better than I do. So now I add a rho phi H, add in the rho phi, but H is H0 plus H prime, the interaction Hamiltonian. Okay, but here, if I treat this H0, H prime, H as H, and rho phi as the interaction, this picture is the Heisenberg picture of H. But it is in the interaction of H minus rho phi. That is, I treating this rho phi as interaction Hamiltonian. Okay, it's a little bit complicated. Okay, evaluated. However, if you follow a little bit, I think again, Professor Coleman did much better than I do. Here, so please consult the lecture notes. But the point is, the first sentence, we are working in the Heisenberg picture of the Hamiltonian and include the H, the interaction in this H, but not the source interaction vertex. Now I can calculate the 0 S0 again, the transition amplitude, the vacuum to vacuum, vacuum to vacuum amplitude, and only treat the rho phi as interaction. Okay, then from the interaction picture, asymmetric calculation, the so-called Dyson formula, this 0, transition amplitude can be written as exponential rho phi time ordered sandwich between 0 and 0. Essentially what I did is to do, let me remind you, this exactly is the interaction picture calculation of S. Let me go back to interaction picture. If you remember, here. So this is interaction picture of S. Did I have a total formula? No, but it doesn't matter. So this is U. If you send this T0 to minus infinity and this T to infinity, then this becomes S. Then S is equal to the interaction Hamiltonian integrated, exponential, and take time ordered. And now remember this HI is rho phi. Because the original interaction has been included in H, we are working in the Heisenberg picture of H. So the only interaction here is rho phi. That's the key. You have to observe this. So only the raw phi is in the interaction. So this formula is obvious. So this formula is obvious that okay. So this formula is obvious. The S could be expressed as the raw phi interaction Hamiltonian integrated and then exponential take time order and sandwich between 0 and 0. Okay, so with this formula, I can of course expand this exponential function in terms of the powers of rho phi, okay, to the nth power, and the term for the nth power will be n power of rho times n powers of phi h, and rho are only C number function, so they can be taken away from the matrix element. So only the phi will stay inside the matrix element, but T ordered. So we got a T order phi hx1, phi hx2 sandwich between 0 and 0. So this guy plays almost the same role as the green function in our answer 2. Do you watch this? However, we are talking about two different things. This is working in the interaction picture, but here we are working in the Heisenberg picture. That's why this phi comes with a subscript of h. This is Heisenberg. So this phi h x1 is a complicated object which is not free and contains all the information of the original interaction. Okay, so this thing is complicated with all the information. It is the hero of the expression. We call it green function or correlative function in the original theory, in condensed matter theory. Okay, so this is answer 3. So this is answer 3. The answer 3 is that if you take again, you calculate this. If you take this vacuum persistent amplitude in the presence of rho as the generating function now, actually you arrived at the phi h, the time order products of phi h sandwich between 2, 0. Sandwich between 2, 0. So this is answer 3. Remember the answer 2. In answer 2, these green functions are actually the sum of all the blobs. So if the answer 2 is the same as answer 3, again, answer 2 working in interaction picture, answer 3 working in Heisenberg picture. If I can equate the two formula, then that means the time order products will be equal to the maybe I use this. The time order products correlation function I listed here is the same as the sum of all the Feynman diagram. So the sum of all the Feynman diagram can be used to calculate this complicated correlation function. That's why the quantum field theory is also useful in condensed matter theory. In condensed matter theory, this thing will be translated into correlation function. And if I can equate answer 2 and answer 3, then it provides us with a tool to calculate this complicated correlation function in terms of Feynman diagram blobs or blob containing Feynman diagrams. Okay, that's the key of all the application of quantum field theory to condensed matter theory. Okay, yeah, so answer 3. So remember, answer 3 is about correlation function in Heisenberg picture. Okay, so yeah, I was probably stop here, but we just one presentation shy of the so-called reformulation or luxury formulation of scattering theory. Remember, our question is, can I reformulate the scattering theory without the turning on and off function? According to Sidney Coleman, we got 2 questions yet to arrive at a reformulation. First, here he summarized the whole thing. He described that the generating function, now if you take the derivative, you arrive at the green function. But here the green function is defined as the green function of Heisenberg picture field operator. So that's why I say this is answer 3. So is answer 3 equal to answer 2? Of course, naively, they should be the same because they are describing the same objects, one in Heisenberg picture and one in interaction picture. So if you believe in the equivalence of the 2 pictures, they are the same without saying. Okay, but are you so sure they are the same? Are you so sure the 2 pictures are equivalent? So Sidney actually tried to answer this in a more subtle way, in a more rigorous way, and the answer is yes. And this proof, this presentation is almost in every on every textbook. What they are trying to write is that this I probably can quote from the Tong, but I will come back to this next week in our presentation. The Tong says this green function is claimed. This green function of vacuum to vacuum sandwiched with the phi 1 Heisenberg picture phi 1 to phi n is equal to the phi I. So this is interaction picture. I will show you next time. The right hand side are the green function from summing the Feynman diagram. So that tells you the summing of Feynman diagrams is essentially equal to the correlation function or the green function of the Heisenberg picture. So that's the Tong's way of saying this. Question 1. Okay. Now, after our presentation, this could be summed up much more succinctly. Is answer 3 equals answer 2? The answer is yes. Okay. And then one more question before we got the reformulation. Is the S matrix is the transition matrix between initial state? Now remember that now we don't have any on and off turning function. Therefore, this K1 initial state and final states are H, eigenstates of H, the whole Hamiltonian, instead of H0. That's the key. So is this S between initial and final state equal to, as we would expect, the green function calculated from this is from the green function of Heisenberg? Okay, the answer is almost yes. If the answer is almost yes, then this green function of Heisenberg operator will be related by the answer of the first question to the sum of all the Feynman diagrams. So again, S matrix in the full picture in the reformulation of scattering theory equal to green function of Heisenberg operator, and Heisenberg operator green function related to Feynman diagram. The green function consisting of Feynman diagrams. Okay, so that means the S matrix is equal to the sum of all Feynman diagrams. Okay, so that's the so-called luxury scattering theory. So next week, I'll continue to tell you, actually the proof of the first one is not that difficult. Okay, so here I have already listed Sidney Coleman's presentation, and almost the identical presentation could be found in Tom's. And the second question, the answer is more complicated. I probably will not go through the detail, but only tell you the final answer and the name, terminology. It is called LSZ, reduction formula. Okay, how LSZ reduction formula. Okay. Yep, it's about 1 hour already. So if you are interested, you can, of course, follow the proof yourself. But I hope stopping at this point will give you a much more a full picture of the argument. Okay, and then we are done with the scattering theory. Okay, but let me present this proof next week so that we have more time to digest. Okay, so I'll see you next week then.